Hello, everyone. Welcome to our breakout session for Build. I'm joined by my colleagues from Microsoft and NVIDIA. Today, we will talk about two interesting use cases where we enabled advanced AI capabilities with Azure Cognitive Services. The first use case is live captioning in Microsoft Teams, and the second one is document translation with mixture of experts model. These are results of joint efforts by Microsoft and NVIDIA, where we deploy AI inferencing workloads with Triton Inference Server and custom optimizations. I'll give a brief overview of Triton Inference Server for context, then we will jump into our use cases. Triton is open source inference serving software to deploy machine learning and deep learning problems at scale. Triton simplifies AI inference deployment by supporting any deep learning and machine learning framework, such as TensorFlow, PyTorch, ONNX Runtime, and TensorRT. Triton also supports various platforms, including CPUs, GPUs, Linux, Windows OS, public cloud, or edge. It has features and utilities to maximize and measure hardware utilization as well. In the next slide, I'm showing the architectural overview of Triton Inference Server. The server part is the big green rectangle at the center of the slide. On the left, we have clients making inference requests to the server. Triton has Python and C++ client libraries supporting HTTP and gRPC APIs. You can also directly link your binary with Triton to avoid communication overheads. And to maximize GPU and CPU utilization, Triton Inference Server supports dynamic batching and running multiple instances on the GPUs or CPUs. Triton supports a wide range of backends listed in the slide. For example, you can have your pre-trained PyTorch or TensorFlow models served with Triton. Or if you want to get optimal performance from GPUs, you can deploy with TensorRT, ONNX Runtime, or faster transformer backends. Finally, Triton gives the users the flexibility to write their own C++ Python custom backends, where you have the ultimate control on how to run and optimize inferencing. And the two use cases that we will talk about today are based on C++ and Python custom backends. With that, I will hand it over to Val and Rakib to talk about our first use case, Microsoft Teams Live Captioning.
Hi, my name is Val Kershin. I'm a software engineer in Microsoft Cognitive Services. And today I'm going to talk about how we used NVIDIA Triton Server to leverage NVIDIA GPUs to reduce the cost of live captioning service, which our team built for Microsoft Teams. And as you might know, Microsoft Teams is capable of providing real-time captions and transcripts for Teams meetings. And that feature is being done by a global distributed service that runs multiple Kubernetes clusters in data centers around the world to perform real-time speech recognition at the large scale of millions of hours of speech across millions of Teams meetings. And of course, doing that requires us to use hundreds of thousands of CPU cores, which cost a significant amount of money. While on the other hand, this service itself is just a feature of Microsoft Teams, so it is really provided free of charge. We don't charge separately for it. And therefore, the service cost is a very big concern for us. But at the same time, we don't want our users to see delayed captions because that's a bad user experience. And therefore, service latency is also our top priority. And before we transition to GPU, in the CPU world, our service at the high level consisted of a pool of speech recognizers, which run the inferencing on CPU, and to which Microsoft Teams sends meeting audio, and which provide recognized text. And this CPU, and to ensure that speech recognizer can keep up with real-time audio, we have to give it enough CPU resources. Because if it don't, then speech recognizer will fall behind and users will see delayed captions. And that is the CPU cost that was the biggest cost driver for our service overall. So to do something about it, Microsoft partnered with NVIDIA to explore the possibility of using GPUs to reduce the cost of speech recognition while still doing it in real time. And in our case, the cost-efficient GPU server has to be able to handle audio for a couple of hundreds of Teams meetings at the same time. And that required a few very specific features which were implemented in Triton. First of all, we needed to be able to scale GPUs and CPUs workloads separately because we don't want GPUs to go underutilized just because the VM that has GPU installed doesn't have enough CPU resources. And therefore, we needed to have a remote service to which we can talk over the network. And then secondly, GPUs really become efficient when they have a lot of data to process at the same time. But individual Teams meeting doesn't really produce enough data to fully utilize the GPU. The speech data comes relatively slowly in relatively small chunks over time. Therefore, to take advantage of GPU power, we need to dynamically combine requests from multiple meetings and send this request as a single batch to GPU to perform inference on. And finally, our speech recognition models are stateful because to be, again, able to do things in real time, we cannot wait until we accumulate enough audio to perform a large chunk of audio and perform inference on it at the same time. We process audio in small chunks, piece by piece, and the processing of each chunk kind of depends on the state that has been built by model during processing of previous chunks. And of course, we don't want that state to be sent over the network back and forth with each request. We want it to be maintained on the server, on the Triton server. And that's why NVIDIA team implemented the stateful backend for Triton specifically to handle this kind of use case. And I believe NVIDIA team is going to talk more about this later on in the meeting. So once we got these features, it became possible for us to switch to this following GPU-based architecture, where we have a separate pool of Triton servers working as DNN inferencing servers for us. And all speech recognizers now send inferencing requests to this DNN service. And this way we can decouple GPU from CPU, we can scale them independently. And this way, we also offloaded DNN inferencing CPU-intensive workload away from speech recognizer. Therefore, we can decrease the CPU requirements for speech recognizer instances, and that's where we actually realized our cost savings. But of course, that didn't come without its challenges. And the most obvious one is that now we have to consider network traffic between speech recognizer servers and Triton servers, which we didn't have to care before. And in our case, the output of each inference request contains thousands of floating point values, which represent probabilities of basic speech elements. Bottom line is that at the rate we make Triton server produce these responses, even 10 gigabit Asian network was becoming a bottleneck, preventing the server from fully utilizing the GPU. And the best way we found to deal with that was to actually modify our model so that instead of this full vector of probabilities, we return only the largest top K of them, with the intuition being that, well, these are probabilities, so probably the largest ones matter anyway, and the rest of them don't really matter. Even though it was a little bit more complicated than that, but that's the basic idea. And this trick allowed us to reduce network traffic enough so that the network is no longer a bottleneck. And another challenge I want to highlight has to do with server shutdown, because when we run the service in Kubernetes can shut down an Triton server instance at any time for a variety of reasons. And the problem with that is that single server instance processes captions for a couple of hundred of team meetings, and more importantly, it maintains model state for all of these meetings. So if it gets shut down at an unfortunate moment, all these meetings are going to lose their state. They're going to have to rebuild it, and that will introduce several seconds at least of latency, which we really don't want. So to resolve this, we actually worked with NVIDIA development team. And I would just want to mention, by the way, that NVIDIA development team has been very helpful. We had great collaboration with them all throughout the duration of this project. I can say, and I can't thank them enough for all their help. And in this particular case, we worked with them to add extra logic to Triton Server to make it more aware of when it is a good time to shut down a stateful model, to reduce the impact on the overall service. And I believe we just talked about it with them on our regular meeting, that this feature has been implemented. It has been released in the latest version of Triton Server. We can't wait to actually test it and use it. And finally, I want to mention load balancing, because again, we need to keep up with real-time data, and we cannot afford to overload Triton instances. Because if we overload the Triton server, then all meetings processed on that instance will get to see increased latency, which is actually going to continue for a period of time because the model is stateful and all the requests for particular Teams meetings get processed by the same Triton instance that maintains the state for that model. And in fact, that instance is going to fall behind more and more, and the captions will be delayed more and more as that instance is overloaded. So it's very important to not overload Triton servers in our case, and we could have just over-provisioned them, but our goal is to cut costs, so we don't want to over-provision a lot. We want to keep Triton server very well utilized, but at the same time make sure it is not overloaded. So we need very precise control over how many requests it handles at all times. Therefore, we can't really use like simple load balancing schemes like round robin or something like that. And so to achieve that precise control, we actually use a token-based load balancer, which is called Southpaw, and has been developed by Microsoft and actually has been recently presented at the At-Scale conference. You can find that presentation probably. And we also proactively scale our service based on historical traffic patterns. Like, for example, we know weekday in the morning, 9 a.m. Eastern, East US is going to start getting a lot of traffic. So we proactively, a few minutes before, start deploying Triton servers there in anticipation of that traffic. And so finally, to conclude, I want to mention that currently this project has been rolled out in production in every region where our service exists and where we were able to get Azure T4 VMs. And for our specific service, for speech recognition teams, the single instance of T4 VM can comfortably actually replace over 60 general purpose CPU cores, which allowed us to reduce our CPU requirements by about 25% overall and reduce our overall service cost by about 20% without like any adverse side effects like latency increase or anything else. So this has been a very great experience for us. We're trying to expand this approach to other services within cognitive services. So that's it for me, and thank you. And I'm going to hand it over to Rakib at NVIDIA team. Thanks.
Hello, everyone. I'm Rakib Hassan. I'm a senior DevTech engineer at NVIDIA, and I'm going to provide some details of the stateful backend that we developed for the speech captioning. As the name suggests, that the stateful backend is a custom C++ Triton backend that automatically manages states to reduce the I/O for ONNX models. It adds some extra features that the Triton default backends doesn't have. Some of those features are, for example, dynamic batching along any dimension of the inputs, FP32 versus FP16 states management, lazy allocation of the states buffer, etc. If these extra features are not needed by your use case, then you can still use the ONNX Runtime backend of Triton, which is a close alternative because of the recently added Triton's implicit state management. And you can find more details on the GitHub page because this stateful backend can be found on the public GitHub. Okay, the stateful backend is written on top of ONNX Runtime, which is a platform-independent framework for running ONNX graphs. It supports multiple execution providers, CPU, CUDA, TensorRT. It can split the graph if needed to run different parts of the model by different execution providers, and each execution providers can be configured with their own customizations. It also allows I/O binding to reduce the inference overhead. As you will see in the next slide, that the TensorRT execution provider is recommended for the best performance from NVIDIA GPUs. In this slide, I'm showing some sample performance with real-time inferencing with Triton, where the server is running on a system with a 8-core CPU and a T4 GPU, and the clients are sending inference requests from a remote system to the server through the gRPC interface. The server is started with the custom backend, the stateful backend, and a stateful model is loaded. The latency and throughput are measured as we keep increasing the request rate from the clients. As you can see, with the CPU execution provider on this system, we can achieve the maximum throughput we can achieve is about 70, where the latency is over 200 millisecond. But let's say if you have a latency budget of 50 millisecond, if you use CUDA execution provider on the same system, you can achieve a maximum throughput of 2400. And if you use the TensorRT execution provider on the same system for the same latency budget, you can achieve the maximum throughput of 3200. And I should mention that this is just a sample performance and not related to how Microsoft Teams uses the stateful backend. I think that's it for me. I'll give it back to Murad so that we can continue with the next section of our presentation.
Thank you, Val and Rakib. It was great to see the value Triton and NVIDIA GPUs bring to Microsoft Teams Live Captioning. Next, we have another very exciting use case, and Henny, Brown, and Young will talk about our second use case, which is about document translation.
Thanks, Murad. Now we are switching to the second use case with the fruitful collaboration between Microsoft and NVIDIA. We will share our work on enabling Microsoft Translator, a document translation feature, with shaping a first-of-a-kind large-scale mixture of expert models. At Microsoft, we have been on a quest to advance AI to empower various products and customers with the most powerful and largest models. AI at Scale initiative at Microsoft is actually focusing on various aspects of modeling lifecycle, including building the models as well as efficient training and inference framework to enable model deployments. As part of Project Turing, we build multimodal and multilingual models that empower various workloads across the company. Today, we are focusing on the code, which provides state-of-the-art foundation models empowering multilingual capabilities for Azure AI workloads, as well as many other products across Microsoft. So why we are trying to build larger models? Actually, we are trying to build much larger models that can cover multilingual and multitask learning. While we are trying to build larger models that can scale up to more language and task, we can easily hit a wall with the scaling. And those scaled models are very hard to deploy in real time. In dense models, all the parameters are being used for all inputs and all tasks at all the times. On the other hand, there is a new family of models which is emerging now called sparsely activated models. In such models, we utilize subset of the parameter for a given input with fixed computation cost. And this fixed computation cost is actually not a function in the total number of parameters. In other terms, we can really scale up the models without paying huge serving and deploying cost for such a large number of parameters. This is a very good fit for the task at hand, trying to model multilingual, multi-task learning for various downstream tasks. That work actually is enabling us to shift our neural machine translation to a new paradigm. And in that third generation paradigm, we are actually getting rid of complex pipelines of the second generation, where we have to distill and to compress larger transformer model into smaller models such that we are able to deploy them on CPU. This limits our modeling capabilities, and actually we cannot have a small model that support multilingual languages at the same time. In that third generation that we are enabling today, we can train very large models, yet sparse models. Each one of them can replace 10 or hundreds, up to 100 models actually from the second generation. And those models have much larger capacity that can support multiple languages at the same time. One instance of that sparse model is the mixture of expert architecture. It can scale up the model by replacing the feed-forward network and utilizing a gating mechanism to control the routing. Each feed-forward network is actually a separate expert that can learn different expertise, which is appealing for multilingual and multitask learning. This actually leads to a very attractive constant number of flops per input. For instance, we can deploy and train 100 billion parameter models while using only 1 billion parameter computation. To enable such a paradigm shift, we actually require very efficient and scalable training framework that we worked with our DBSpeed team to achieve that. And we are requiring very efficient inference runtime that is more optimized for sparse models. And now I switch to my colleagues, Yon, Jen, and Ron, to share with you how we did achieve such a milestone.
Thanks, Sunny. Here, I'm diving deeper into the limitations of the current generation and why we are moving to a new generation with larger model sizes and multilingual multitask settings. In the figure left, only the red base-sized or small-sized student models were shippable with the current pipeline on CPU. Heavy knowledge distillation and sophisticated model compression steps are required to maintain the similar quality as teacher models, which are in blue squares in the figure. 10 different model training steps are required for just one language pair translation. And this needs to be done for 200 different language pairs. This independent training is also not desirable because it couldn't really utilize the power of transfer learning, and especially low resource languages will suffer from all those steps. Even with these very sophisticated steps, it's hard to avoid the quality degradations perfectly. Now, with the multilingual model settings, we need even much larger model capacity. As you can see on the right-hand side, any models we train with multilingual settings are much larger than even teacher models in the knowledge distillation setting. So we again need a more efficient way to build and serve those large-scale models. As previously discussed, the mixture of expert architecture can scale the number of model parameters without increasing computation much. As you can see on the right-hand side figure, only a part of whole parameters is activated for a given input by a gating network. This increases the model scaling efficiency significantly. Meanwhile, in order to achieve the best model quality, we need to combine various kinds of parallelism together. Expert parallelism expert parallelism with MoE is just one way. In deep speed library, we could combine multiple different parallelism such as data parallelism, zero optimized parallelism, and model parallelism together to train the best models more efficiently. As you can see in the table, left-hand side table, you can combine many different kinds of parallelisms together. So we work together with DeepSpeed team to make this MoE training more efficient. As a result, as you can see in the left-hand side figure, we could achieve train 8 times bigger model in the same number of GPUs, or the same size model with only 8 times fewer GPUs. On the right-hand side figure, we achieved almost linear scaling in terms of throughput when we increase the number of GPUs. With this very good system scalability, we started to train our multilingual multitask models with mixture of expert architecture. The result is very impressive. On the left-hand side figure, you can see the validation cross-entropy loss converges faster to a lower value when we add more number of experts compared to the blue line, which is the dense model. On the right-hand side figure, mixture of expert models, which are orange colored, get much more benefits from multitask training. Here, dotted lines are single task training and solid lines are multitask training. With dense model, which are blue lines, didn't get much improvement with multitask training. However, with MoE models, we could achieve much better validation loss and training curve with multitask training. This again verifies our direction is correct. So by applying all those improvements with multitask, multilingual MoE models, we applied it to the machine translation scenario. And we could achieve much better translation quality all across 26 language pairs, which are the first phase of our production models. Here, y-axis means the relative human evaluation score improvements, and the x-axis means different language pairs. I'd like to emphasize that just one multilingual MoE model could replace about 10 separate models. With the much better models with multilingual MoE, we started to build a new production pipeline. The existing production systems were all CPU-based, so we needed a way to manage GPUs in a scalable way. Thanks to NVIDIA's Triton Server and Azure ML's auto-scaling, we were able to build a scalable pipeline. When the customers hit the document translation API, the queries are routed to the Azure ML endpoint. And inside the Azure ML, we built 2 kinds of containers, which are empty pre- and post-processing container and Triton Inference container. Thanks to the dynamic batching from Triton, we could utilize GPUs in a very efficient way by increasing the effective batch size. And Triton's model management enabled us to manage large-scale MoE models efficiently. The remaining challenge was how to make these MoE neural computations more efficient. With the initial implementation of MoE, it was up to 30 times slower than highly optimized dense models. So it was really challenging to design various new kernels and layers. So we worked together with Ron to tackle this challenge. I'd like to hand this over to Ron for some more details.
All right, thank you, Young, for the introduction. I'm Ron. I'm a senior AI dev tech engineer at NVIDIA. And I worked with Microsoft to help optimize this mixture of experts model. So essentially, what we did is we leveraged optimizations that already exist in our public faster transformer library in order to serve this model cost effectively. Our faster transformer natively gave us a very optimized implementation of beam search, optimized attention kernels for standard attention, and optimized decoding kernels with efficient caching to reduce redundant computation. We had to make two small additions to our runtime backend to efficiently support mixture of experts. The first is special attention kernels for tube attention. And the second is optimized kernels to run the mixture of experts layers efficiently. For that, we used a combination of Cub and Cutlass. And essentially, after adding these two optimizations to Fast Transformer, then we benchmarked against Python, just PyTorch libraries running mixture of experts. And we were able to achieve speedups seen here. So basically what this chart shows is speedups over PyTorch when running mixture of experts models on a V100 in FP16. And the x-axis is a combination of batch times beam. So I ran a variety of batch sizes, and I have beam widths of 1 and 2. So as you can see, for large batch, we get a bit over 12x. And for small batch, in the best case, you get a bit over 27x. So you see, we have substantial speedups from our optimizations using this faster transformer backend. And that makes serving these large models very cost efficient. In fact, it allows us to serve models that are over 80x, that have over 80x more parameters, while achieving an 18% reduction in runtime costs. And as Young mentioned, one of these models replaces tens of models and tens of CPU instances. It was possible to serve these models thanks to Triton's flexibility because it supports custom backends, and we'll do a bit of a deep dive into that. And to use our custom CUDA kernels with faster transformer, we just exposed them to Python using Torch custom ops. So Murat showed you earlier the overview of Triton, so I won't go over everything in the overview, but I just want to highlight the simple change here that you need to make in order to use a custom backend. So all you need to do is, I think the original slide had a bunch of different backends as options. So all you need to do is just write your own custom Python backend, and it's just like a plug and play thing. And now your backend will sit behind Triton. Your backend will take in the requests, run inference, and send responses back to the users. And with your backend, you still get all the nice capabilities of Triton, such as like throughput, latency, and utilization metrics. And now I'll do a bit of a deep dive into the custom Python backend. So there's this simple API that Triton exposes in order to plug in your backend. So the first is that you must create a class, and your class must be called Triton Python model. And inside that class, there are 3 functions that you must define. One is initialize, and that basically just sets up the model state. So here in the bit of pseudocode here, one thing you could do is just load your model from disk if you choose. The second is a function that executes the model. So that's where the neural network inference is run. So you can see that just takes a list of requests and returns a list of responses for each request. And I should note that the list of responses must be equal to the list of requests. So you could do pre-processing inside there, then you could run the model evaluation, which is what this is showing. Then post-process, then maybe you might want to convert your model. You might want to convert from your neural network outputs back to a list of responses, and then you return the responses, and Triton will handle sending them back to the user. And as a final step, there's a finalize function where you free up any model resources that the model may be occupying on CPU or GPU. And with that, I also would like to note that Triton also supports C++ backends. We chose the Python custom backend because it was simpler to implement, and we had access to more libraries to do pre and post processing. And for more details here, please check out the section in the resources about writing a custom Python backend in Triton. There's also a link for writing C++ backends if that's what you're interested in. Thank you for listening, and I will hand back to Murat, who will give some closing remarks.
Thank you very much, Ran, Yang, and Henny. It is very exciting to see the impressive accuracy improvements for many languages using a single MoE model. And equally importantly, I'm glad that we could work together to create an efficient implementation with Triton on the GPUs. And I'm really looking forward to continue our collaborations with Microsoft to enable additional use cases with these state-of-the-art models. With that, we're going to close our session and we'll be available for question and answering. And as Ran mentioned, if you like to check the various things that we touched on today, please check the resources section of our build session. And thank you very much for your time.